Hello there, welcome to another tutorial. In this video we're looking at SUVAT and how to actually derive SUVAT from scratch. So when it comes down to SUVAT, what we're looking at, if we look at initially at a graph like this, we can see the displacement r and then we have the time t. And you might follow a curve like this. Now, when it comes down to it, the velocity we know is going to be tangential, a tangent there. That's going to be the velocity, and if we actually get 2 points as a triangle like that, I mean, I'll draw that in a separate part. If we look at the line, the tangent, the instantaneous velocity, we can get the line like this. And we know that there is going to be change in time. And then we know this here. We know this point here is going to be, we'll call it r of t. And then we'll call this point here r of t plus change in time. So we can therefore write it as a gradient. So we know velocity is going to equal r of t plus change in time. It's the simple gradient. So it's the higher one minus it's the two y values minus r of t like this over change in time. So we know that to be true. So velocity is equal to that minus that over change in time. And then if you want to look at, however, we know. If we look at that again, we know as change in time approaches zero as a limit. This is just the derivation of the fundamental theorem of calculus. We know that that's a derivative, or at least that's a derivative. I'm not sure exactly that, but it's the derivative of a derivative, you know. So it's going to be sorry, that's quite funny. Therefore we know that's going to become dr by dt. We know that's as a thing. And it's the same for acceleration. If you look at a graph for acceleration, let's say we put it here. Acceleration, time. Now, in a lot of SUVAT problems, you'll generally have a constant acceleration. But let's say, not acceleration. It should be velocity, sorry. In a lot of SUVAT problems, you will have a constant acceleration. But let's just say for this instant we don't. It's just this, a random curve. Again, you get the tangent, and as a triangle again, it's the same thing. You're therefore going to get a similar thing of acceleration is equal to velocity of time plus change in t. Like this, over change in time. And we know that again, as change in t approaches zero, it actually becomes, the actual way of looking at it is it'll become dt, an infinitesimally small change in time. So therefore, again, in the form acceleration is equal to dv by dt. Now we know again, we actually know that velocity, let's go here. We know that velocity is equal to dr by dt. If we therefore know that acceleration is equal to dv by dt, all we have to do is differentiate the velocity. So that's going to be, we know therefore acceleration is going to equal d by dt of dr by dt. So we differentiate that. So acceleration is equal to the derivative with respect to time of dr by dt, and that's just going to equal d squared r by dt squared in that format there. Now SUVAT, if we actually want to look at SUVAT, we want to define it a bit more. So we know with SUVAT that we know that the first equation, velocity is equal to dr by dt. If we want to get a SUVAT equation, what we need to do, we need to basically rearrange it into this form here. So we're going to have v dt is equal to dr, and we'll turn it around, and therefore we know the integral between, we'll have the initial displacement, and we'll have then the r value, then we'll have the current displacement again for dr r is equal to the integral between 0 and t of v dt, like that. That's the format we get it into. Now when we integrate that, we're actually going to get it into this form here, r, because again the integral of 1 is just going to be for dr is going to be just r. R is going to equal vt, because again that's vt between 0 and time. Now that's just quite simple. That can just convert into r minus r0 is equal to vt, and you can see now we have this. We have a SUVAT equation. We know that the displacement is equal to the initial displacement plus velocity times by time. That's an initial SUVAT equation that we have. If we then want to get another one, we can do acceleration now. Acceleration is equal to dv by dt. So dv is equal to, that's not very clear, I apologize. dv is equal to acceleration dt, like that. The integral between v0 and v for 1 dv is equal to the integral between 0 and t acceleration dt. And then what we're going to do is that's going to again be v for the 0, like that, is equal to at, not the clearest, I apologize, between 0 and t. The next part now, what we want to do, v minus v0 is equal to, let me just see, at, and you can see we have SUVAT here now. SUVAT, v is equal to v0 plus at. SUVAT there. You can see that that's another SUVAT equation derived. This is where it all comes from. It all comes from the calculus. That's where all SUVAT comes from. If we then want to look at another one, we'll zoom in there. Now for the next equation, what we have is acceleration equal to, remember, d squared r by dt squared. Now, what we need to do with this is we'll start again with the dv by dt first, just to do the first integral. It's the same thing basically, but it's equal to dv by dt. And then we get dv, remember the integral between v0 and v is equal to the integral between 0 and t, because it starts at time equals 0. I mean, you could put t0 if it doesn't start at time equals 0, but we'll assume it starts at time equals 0 to keep it simple, and generally in problems it will start at time equals 0. That makes more sense. We then have acceleration dt, and we already know what this turns into. This turns into v equals v0 plus at. We derived that before. The next part is the part with the we know that v, remember, is equal to dr by dt is equal to v0 plus at. Now we can get it into this form here, integral between between r0 and r is equal to the integral between 0 and t for v0 dt plus the integral between 0 and t of at dt, like that. Not the clearest, but you can see now we've got it into this integral form. That part's wrong. That should be dr. I apologize. And again, that's just one. That's just that, it's just one in there. So then the next part, for this part, you can actually just integrate it quite simply. We'll go to another part of the page, and we'll go over here. So again, it was the integral between r0 and r of dr is equal to the integral between 0 and t for v0, the initial velocity. It could be initial. It could start from rest, so v0 would equal 0, plus the integral between 0 and t for the acceleration term and dt. Now, to integrate this, it's going to be, of course, r, like this, because again, it's 1 in there, between r0 and r is equal to v, 1 second, let's make that clearer, between v0 times by t, between, again, 0 and t, plus, it's going to be, sorry, that should be at, not, that should be at, sorry, not that. Now, the integral of t is just going to be t squared over 2, so it's going to be at squared over 2, like this, between 0 and t. Now, that's fairly simple. You can just get it into this format here. It's going to be r minus r0 is equal to v0 t plus at squared over 2. Now that's pretty useful, that. We have it in that format there. If you want to get it into the actual SUVAT famous way, you want to get into r equals the initial displacement plus the initial, that's not very clear. I want to keep it very clear, hopefully. Plus the initial velocity times by time plus a over 2t squared. Now, in many problems, a might be equal to g. It might be equal to, for example, if it's a gravity problem, if it's a falling problem, then you might write it like this. It might equal the current displacement is equal to the initial displacement. Let's say it starts at, you might see it familiar here. Let's say the initial height of let's say the particle. Let's say, actually, let's make it clear. I'll show you how it can be applied. So let's say we have a particle here, and it's falling, and it starts at a height. It starts at a height of h. So it starts at a height of h. Therefore, you're going to have the current displacement is going to equal h plus, and let's say the initial velocity is 0. If the initial velocity is 0, then obviously that's going to just be this part here is just going to be 0. So it might be h plus, and then if it's gravity, it's going to be g over 2t squared. And that's the formula we have there, because it's true. The initial velocity could be starting from rest, and therefore we know that it's going to be the current updated position is going to be that, and if it is falling, it should be minus g. If it's falling from rest, it should be minus g, because gravity is acting downwards, and if we're going to resolve upwards, because if h is positive, it means that we're resolving. If h is positive, it means that we're resolving upwards, and that's very important. Resolving is a very important thing to understand in mechanics. I'll show you why. Let's say we have the ball here and it's fallen down, right? So it's h. If the ground's there, then h is going upwards. We're resolving upwards there. We know gravity is going downwards always. If you resolve that way, therefore when you write out the equation, let's say the initial velocity, it starts at, right here, the initial velocity is going to be equal to 0, then with that equation, we know that we're going to get it into form of the current displacement is going to equal r0, which we know is h, plus, and this v0, remember, if v0 is 0, then that's going to cancel out a term. You're going to have 0 times by time, which is just 0, so that part isn't going to matter. So it's going to plus, however, it's going to be minus g, because it's gravity is acting downwards, and we've resolved upwards. So it's going to be minus g like that, times by time t squared over 2 like that. And that's really important, that relation. And to actually, let's say you want to solve that, you get it into a form like this. You have r equals h minus g t squared over 2. This is, we've already derived SUVAT, but it's just showing how it can be applied. And if you want to solve that, you simply just you rearrange it into this format. I'll show you. G t squared over 2 is equal to h minus r, like this, gt squared equals 2h minus r, like this, and t squared is equal to 2h minus r, like this, over g. And then finally we get into the form of that, and then with the square root it's going to equal plus or minus the square root of 2h minus r over g, like that, square root like this, square root there. So you have it in that format there of that h minus r. That is assuming that it starts from rest. However, if it doesn't start from rest, it is going to be slightly different, of course. That's the general way that you can use this. But you can see, it's all derived from integration and calculus. That's where it all comes from. SUVAT. Initially, when you first start learning mechanics, you might not actually look at the calculus part of it. You might just look at the SUVAT formulas and you sort of wonder where it comes from. But it's important just to remember that relationship between that acceleration is the derivative of velocity and the second derivative of displacement. Once you know that relationship, you can then solve harder problems in mechanics. And I would say with mechanics, it's worth understanding. Don't just be able to apply it. Understand where it comes from, and then you can get a much better. Things will fall into place a lot faster if you can really understand where it comes from. Because this is using all kind of problems. All problems are going to require this. But yeah, thank you for watching. Hope you enjoyed, and please consider subscribing. But yeah, thank you.